Welcome to this edition of On Track, our whiteboard video series. My name's Ben Jordan, and today I want to do part one of a multi-part series on multi-board PCB design. Why is multi-board design important? Why is it an issue we have to talk about like this? Well, pretty much every PCB designer is going to have to design boards that go into systems integrating with other boards at some point if you're not doing it already. And so I wanted to provide some thoughts, some tools, some techniques for making this a successful endeavor. Today, in part one, we're going to talk about partitioning. So multi-board designs and systems, for our definition, for our purposes in this series, is any kind of assembly where there's more than one actual printed circuit board. And so they may be different boards, like here I have a sample of an example illustration of a power supply design. Here I've got an Arduino with a few shields. Here I have like a mini computer motherboard kind of thing. And really there's kind of three ways of partitioning designs when you have to make a multi-board system. And which method you use really depends on why your multi-board system has to be a multi-board system. So what are the reasons we need to partition? A pretty common one is physical form and fit. That obviously doesn't apply necessarily to an Arduino stack, but it certainly applies to something like this power supply here, where we may have a physical sort of constraint that requires a certain enclosure size, thermal considerations, etc. And in order to fit all of the complex control circuitry for the power supply, maybe we have to do it on a sideways mounted module. I've seen this is quite common in power supplies actually. But there's another reason for that, and that is obfuscation. So we have physical form and fit, and we have obfuscation. This is using modular design approach in order to hide things about your design and protect your intellectual property. Back to this power supply example, I actually have seen firsthand supplies where the controller devices were all on more complex small PCBs mounted vertically like this. And this allowed for isolation between primary and secondary on the power supply. It also allowed for complex control circuitry to be hidden from the end user. All the chips were potted in a very thick compound. It was difficult to reverse engineer. So that is another method. In the case of the Arduino stack, that's a good example of compatibility. We want to make something really easy to get, pull different modules in together to get the functions we need. So modularization allows for rapid prototyping and creating some sort of one-off custom product using different functions. And so in this case, we modularize using a standard sort of, maybe a de facto or well-defined standard, either way, some kind of standard pinout and shape and physical configuration with signaling, with power supplies, etc. But doing it in a way that we can create something very quickly and know that it will work pretty much first time. And we have the same kind of thing going on in this case with something like a PC motherboard with a mini PCIe socket here, or PCI slot, or USB or anything like that. We can very quickly create a custom configuration. So one approach, one reason for multi-board designs is configuration management of and mass customization of our product. And so these are the different thinking or reasons why we do multi-board design. Some other reasons, perhaps there's a section of the circuit that's quite complex and difficult to make, or requires a more expensive PCB. So one other case, and going back to my power supply example again, maybe the main board's just a simple 2-layer, 2-ounce copper PCB for heavy currents and basic switching circuitry, but the controls need a 4 or 6-layer PCB because we have a very complex control algorithm running on a high-speed microcontroller. And this would be a very common case with an industrial inverter driving motors, for example, where you really want to measure a lot of things and you need more power in that PCB. So this gives you an option to make one smaller PCB for the expensive bit and keep the rest of the design much cheaper by doing simpler printed circuit board manufacturing technology, simpler layer stacks. And so these are the driving motivations behind behind these partitioning methods. Dumb cut, I call it, functional blocks, and standardization, or using standards. So let's go through these really quick. This is my term, dumb cut. It's not an industry term, but I'm just making it up because I can't think of a better way of putting it. But this is what you do when you have a physical requirement driving your decision and you have a certain size printed circuit board enclosure. So let's just do an enclosure here, for example. In this 2D view, let's say my product has to fit in that kind of physical space looking at it from the top down. So I may just choose to cut my board right through the middle, redo my designs to have some things move over on this side, some parts move over here, some parts move over here, provide some room. And this kind of partitioning is often done starting in the schematics of an existing board and then separating it out into PCB projects. But this has a number of pretty big disadvantages, hence my term dumb cut. One is that you can end up with really strange signal paths. Signals may wind up going through. So for example, in this design I have a power input jack here. This is my power supply input and switch. And then we have the power supply circuitry is all kind of in this area here. Right, so some of that, obviously we can't allow that to stay on this side if we're going to essentially divide this down into two PCB designs down the middle. So we end up with, we have some high-speed digital circuitry for HDMI and Ethernet ports over here. I have this section here has the PCIe connector and some RF, Wi-Fi connectivity or whatever. Down here I have a couple of analog front ends with some, noise sensitive IOs with these SMA connectors. Maybe this is some kind of high-speed digital interface or another RF interface. But for now, let's just say it's sensitive analog circuitry. And here I have my CPU and memory and all of the basic digital stuff. So already we're mostly in a position on this design where it's easy to cut things up because of the different functional blocks. However, I have seen real world scenarios where we had, just one example, a motherboard with some audio connectors going to another connector with a module on top of that that had an audio codec chip on it. So my analog audio went back to there, and then the digital interface of that audio codec chip came back off here and went to an FPGA on the motherboard. And separating the connectors, this is the main input and output for that interface. This is the CPU or FPGA device doing the signal processing, and yet for some strange reason we put the codec on a separate module. No real rhyme or reason to that, but this is the kind of crazy thing you can end up with when you take the dumb cut approach. So unless it's a physical constraint, not really a good idea. So what's the next one? Functional block. This is the approach most people take most of the time for partitioning multi-board design. And it essentially it's like driven from your system block diagram. So over here we may have the CPU and memory. There's our CPU and memory block. And then we have some kind of interface connections. And we have RF and analog over here. Then we have on this side, we might have Wi-Fi or Ethernet. You know, basically our digital connectivity and IOs. And maybe some user interface I/O in another block. So user I/O. And then there might be well then of course, to power all of these, we have a power supply. So let's call that the power supply unit, or PSU. And so the functional block approach is the typical sensible approach to partitioning. And we would do that in this case really because we have our PCIe I/O here, we have Wi-Fi, analog I/O and RF, telecommunications and video interface, power supply. So we're kind of already going down that road, and this would be a more typical way to do it. The advantage of doing the functional block approach is, apart from regular modularization benefits, is that for this part of the design with the CPU and all the memory and other high-speed digital stuff, we typically need those things to have maybe at least a 6-layer board, often more like a 12-layer PCB for all of the routing and all of the power planes and return paths to make a good EMI performing high-speed digital board with a CPU. And then over here for the analog and RF, we may only need 4 layers. And we can even go as far as to say we could use different printed circuit board materials for that module if we need it. And that can save some cost and make it easier to test everything as separate modules. Then similarly, we have our PCIe. So let me just come back here and talk about standardization. On the topic of PCIe and the Arduino example, even though this is not a hard industry standard, it is a de facto standard. The advantage of these approaches to partitioning is, on this case, we have a very simple way. It's fairly well defined, and there's a lot of good content in the industry already that allows us to design just one module in the overall system, and we can reuse other stuff to our heart's content. We could take a standard CPU on an Arduino baseboard or compatible. We could take other off-the-shelf shields to get different functions that we need. There's plenty of contributors to the community. So this has the advantage of being open and being easy. It has a lot of valuable content already out there done by and shared by people in the design community. So all we have to do is focus on our specialized small piece and just get that right. Makes it a lot easier and cheaper for us to build systems around that. And the same would go for things like PCIe 104, sodium, or not sodium, there's different card standards out there for single board computers. And so all of these have this benefit of we don't have to do everything ourselves. We can just do the little bit that we want to do. And similarly for things like standards like PCIe or PCIe, mini PCIe like this one here, we have the benefit of predefined connectivity, pinouts, and signaling and handshaking systems that mean as long as we design to the standard, we know it's going to work. Electrically, it's going to work. It's not going to have problems. And so in an upcoming episode, we'll talk some more about the different standards we can use when doing multi-board designs and what some of the pros and cons are. And we'll also talk about connectivity solutions and connection management, because there are, depending on what the performance aspects are of your design, there are different needs and requirements for electromagnetic compatibility, and there are potential signal integrity and power integrity issues as well. And your choice of connectors and signaling schemes has a profound effect on the performance of your design from those aspects. So in future episodes, please stay tuned for talking about signal integrity, power integrity, connectors and connection management, and different standards for multi-board design. So hopefully this has been helpful. If you find it helpful, please like, share, subscribe to our On-Track video series. If you have any questions or comments, please put them down below here in the comments section. I've been Ben Jordan for On-Track, and thanks very much for watching.